black hole for Physics 2211 Georgia Tech. So in this video, I'll go over the introduction, the purpose of the lab, formulas we'll use, the experiment and data, the glow script and its model, the discussion of possible errors, and our conclusion. So the purpose of the lab is broken down into two parts. In part one, we analyze the motion of a star to determine the mass of a black hole. In part two, we simulate a planet-moon ship system and obtain an initial velocity of a spaceship. So the ship is affected by both bodies, which means the flight orbits the moon while the moon orbits the planet without crashing or being sucked into the black hole. We'll visit the momentum force, the gravitational force, and Newton's second law. So the formulas we'll use is the gravitational force, so the force due to a planet's gravity, the momentum principle, which you've used many times, and then Newton's second law. Here I showed you guys the breakdown on how we can get the parallel and perpendicular components. So this is your parallel component right here, and this is your perpendicular component right here. And this is essentially a description of what Newton's second law says. So part one, we just modified the starter code, and then we found it out after averaging out all the values, we get the mass of the black hole to be 1.35711 times 10 to the power of 34. Here's what it looks like. And we know our orange arrow is Fnet, our cyan arrow is Fnet perpendicular, and our magenta arrow is Fnet parallel. Our system is the star black hole, and our surroundings are everything else. So here's the part one code analysis. Essentially, on the left is our initial values that I placed, and then I use a time step of 86,400, which is the number of seconds on Earth, basically, in one day. And then here is my calculation loop. First, to calculate the trajectory, I calculated the initial and final velocity vectors. Then I calculated the initial and final momentum using this. I calculated dp dt, which gives us the net force, based on Newton's second law. Then I split the net force into its parallel and perpendicular components. Then I computed the inward radial component of the net forces. I then used Newton's law of gravitation to estimate the black hole's mass at the instant using this equation right here. Oh, sorry. And then I stored each mass estimate into a list so I could average them out later. This loop also gives the visual arrows, as you saw in the video, of the cyan, orange, and magenta. And this is basically my residual error force, and then how I made the arrows stand out, because I just use arrow scale, error boost, and error cap basically to make the arrow stand out, visible. Sorry. In part two, we got our initial velocity vector to be negative 700, 450, and 0 meters per second. And we again modified the starter code. So the cyan is the orbit of the moon, magenta is the orbit of the spaceship, and our system here is the planet moon spaceship, and our surroundings are everything else. So here's a part two code analysis. To the left right here is all of our initial conditions. I basically just set our ship's speed to be negative 700 meters per second, and our ship's y speed, sorry, that was the x speed, this is the y speed, to be 450 meters per second. And these values give the trajectory that loops around the system without crashing during the simulation times. These are the times I chose for myself. Here is my calculation loop. To calculate the net force on the moon, we find the force on the moon due to the planet and the force on the moon due to the spaceship. And then I added these together to get the net force. And although the planet is the dominant force, the ship's gravity still has to be taken into account because of the directions. The net force on the spaceship is the force on the ship due to the planet, and then the force on the ship due to the moon, and then add them all up. This is what makes the ship's path depend on the bodies instead of just orbiting around only the moon or only the planet. And then updating the motion here, after finding the net forces, I'll update the velocity using the Euler-Kromer method. And here's the two new position and new velocity methods that I use. And then I let the simulation predict how the objects move forward in every step of the time. Some possible signs of error would be limited precision with rounding, human error for picking inaccurate values, and larger time steps causing inaccurate forces. So our first question is how the net force and its parallel and perpendicular components are different from the rate of the change of momentum and its parallel and perpendicular components. So the net force is the total physical interaction on the star, while the rate of change is a momentum that we infer from the star changing motion. In Newton's second law, these are numerically equal. So the parallel and perpendicular components also match. The parallel component changes the magnitude of momentum, which changes speed, while the perpendicular component changes the direction of the momentum, which bends the orbit. Our second question is, if you wanted to predict the motion of the entire system, what would you need to use to include in your computational model? To model the whole system, I would need an n-body simulation where every object exerts a gravitational force on every other object, and all positions and velocities are updated over time. I would no longer keep the planet fixed because in a full model, every body should be allowed to move. The forces would all not contribute equally because some are greater, some are less mass. The dominant interactions would likely be the black hole on the star, and the star on the planet, and the planet on the moon, and the planet on the moon on the starship. Planet and moon on the starship. More distant bodies would still affect the moon, but they would have a smaller effect. Thank you.